Hello, welcome to the Henstitute. Today we are going to be talking about Chapter 11 on fluid statics dealing with pressure. So in this particular section, we'll define exactly what pressure is. We'll try to get into how it is applied. It's even going to relate to Archimedes' Principle when we eventually get there. So to start off with, what exactly is pressure? So pressure itself, let's see if I can move that out of the way. There we go. Move myself up here. Hey, I'm going to put myself right there. Pressure itself is defined as my force per unit area. So we're going to use a capital P for pressure, capital F for force, and then a capital A to represent area. So this is going to be our equation. The unit, our standard unit for pressure, is actually going to be the Newton per square meter because force and areas are that way. And this is sometimes referred to as a Pascal, so it's labeled with a PA. Now, interestingly enough, pressure doesn't actually have a direction. It's not a vector, even though force is a vector. And I like this little picture over here where they kind of represent this small little box inside this tire of air. And if you look at it, you have forces acting on different directions. So if I look at that particular force in this particular area, I can find the pressure acting on it, but it's not actually, we're always looking at the force that is perpendicular to the actual area that we have. And so when we're trying to find the pressure inside of something, we're just looking at a particular force on a particular area and not over the whole thing. Example, let's say that we have a swimmer and they're swimming through the water, and it says the pressure acting on the back of a swimmer's hand is 1.2 times 10 to the 5th pascals. The surface area of the back of the hand is a very small number. That's 8.4 times 10 to the minus 3. We want to determine the magnitude of the force and the direction. Now I'm going to start off with direction because I can actually relate that here, and it's actually in this picture already. So if I'm trying to find the force on the back of her hand, since her hand is going to be like this and the force is going to be acting downward on it, that would be the direction of the force to find that pressure. And then you go, okay, wait a second, why doesn't her hand get pushed down then? Because we could also find the force acting up on her hand, which we could figure out. We could figure out how much force is pushing direct sideways on our hand on all these directions. So I like this picture over here where they show on a particular section of the body, you have forces acting in all these different directions. Then we can plug in our numbers. Now I'm going to point out this particular equation. So when you rearrange this to solve for force, we get force equals pressure times area, or F equals PA. I think this is hilarious because back in chapter 2, we had F equals MA, or FMA. So force equals not only Ma, it also equals PA. So we have both of these. And then we calculate everything out. We've got our numbers here. And what you find is you've got your pressure and you get 1,000 newtons. And you're like, hey, how much is that? I don't know how much that is. Well, if I divide this by 2.2, you're going to be pretty close because there are about 2.2 newtons per pound. So that would change it into pounds. So I'm going to do that over here, 1,000 divided by 2.2. And you get 454.5. So again, this mentions like, oh my goodness, 454.5 pounds is pushing down on her hand? Yes. 454.5 pounds is pushing up on her hand? Yes. 454, so it's pushing in all those directions. So it doesn't really matter. Actually, a different force is probably going to be sideways because it's going to be a different area, but top and bottom would be the same. Atmospheric pressure is amazing. Let's move my face again. And the atmospheric pressure at sea level is this 1.013 times 10 to the 5th pascals. And this is coming from the fact that if you had a base that was 1 square meter here, it would actually have a force of this much. So 101,300 newtons of force. Again, let's divide that by 2.2. You're talking about 46,045 pounds of force. So this is amazing, the amount of force that is down acting on every surface. So if you had a square meter, which is a pretty big, because a meter is about 3 feet. So you're talking about 3 feet by 3 feet. So you're talking about approximately a square yard, somewhere in there. You're talking about a fairly big little section. It would have 46,000 pounds of force. Now I put this little video in here that's called Imploding Drum. It's from the YouTube channel Veritasium. I'm a big fan of Veritasium. I'm not going to play it here, but I put it as a reminder. It shows the power of this. The reason why we don't get crushed like this little can over here is because we actually have pressure inside us and outside us that are equalized. And so the example is if you can get rid of that internal pressure, outside atmospheric pressure could crush things. It's amazing. This one's also a good one to kind of get at the idea of what we have going on. I'm going to move myself again. So if I take a little section of some fluid here, this one's kind of a picture, and I snatch it, what I can look at is the fact that this object, if it's static, meaning it's not moving, then we should have all the forces acting on it should equal 0. So downward forces, we have a pressure force pushing down, which we can write as PAW, P1A, and then we have the weight of the object, so there's our weight acting on it right there, and those two acting down should be balanced by some kind of upward force. They call that F2. So that's kind of what this is written out as. I like to write it like this, where you have them equal to each other. Then the next step, like we saw from our density stuff, we can replace mass with volume times density. And so we get another little advantage of that. You can change your equation a little bit. I keep being on top of stuff. So I have rho VG here, which is kind of our equation. Then I can replace my volume with the area multiplied by height, because if I think about this as a rectangular solid that has a certain height, it's really just the area of the top times that height. I was mentioning this before. And so you end up with rho AHG, and then I can cancel out all of the areas because all the areas are the same, and you end up with this neat little equation. What it tells me is that the pressure at the bottom of some fluid is equal to the pressure at the top of the fluid plus rho times the height of it. So if you have a certain height that's acting there. And so as you go deeper into a fluid, you're actually going to have more and more of this particular pressure. So Hoover Dam is a great little example here. We know Hoover Dam has all of this water back here, so it's got to support all this water. The interesting thing is it doesn't actually have to have all that water. All you need is this thin little narrow column of water, because as you go deeper into that fluid is where you get a greater pressure. So the pressure down here is much greater than the pressure up here, just a little pressure. And so you still have to create a dam with this little shape here where it's much thicker at the bottom than it is at the top. Doesn't matter if it's a small little section or if it carried on for a whole bunch. The pressure doesn't depend on the horizontal part. It only depends on a vertical part, basically because of the weight of the fluid pushing down. So how would I find the pressure at a particular point if I was a certain depth in there? First off, with this little question, I think it's kind of neat to realize that both A and B would be the exact same pressure because they're at the same depth. It doesn't matter horizontally where they are. So if I'm applying this equation, P2 is what I'm actually trying to find here. So I need a P1. Where's my other point? So a common place is to pick a point that you know. If I was talking about like an ocean or a lake or something like that, I know at the top here that the pressure there would just be air pressure. And so I can replace my atmospheric pressure here. They just didn't write the 3, but 1.013 times 10 to the 5th pascals. And then I've got the density times gravity times my height or my depth. And I'm going to use H, but it's still really a depth, and I can get the pressure at that bottom section. It's going to be higher. We use this all the time when we're trying to find the amount of pressure of air. So a thing that we often use is a thing called a manometer here in chemistry and physics. manometer. Manometer, and what it is it's basically it's like a giant tube, so it's like a giant test tube, and you fill with some fluid, and then usually you invert it in the fluid itself. So that's what they've done here, is they have mercury that's inside of this thing, and then it's flipped inside of a tub of mercury. And so the idea is, as the mercury falls, it's going to leave a section up here that's basically empty. So it has zero pressure up here. And if there's zero pressure, then P1 is going to disappear. Down here you have P2, you just have air pressure pushing down, and it holds this fluid up to a certain height. And the height of this is what you can find here. Now, really what you're talking about is we always flip this. So remember, we've been doing P2 as the lower point and P1 as a higher point. So it's really H is kind of like the depth of the fluid from where you have zero pressure. And you can rearrange that to solve for H, and you get this 760 millimeters of mercury, which is a common phrase for atmospheric pressure being 760 millimeters of mercury, 760 torr. Things like that. So it would be about 3/4 of a meter tall. The interesting thing is, if you were to place this with water, what you would have is you'd still have the same top, 1.013 times 10 to the 5th pascals. And then on the bottom, instead of the density of the mercury, you would have the density of water, which is 1,000 kilograms per cubic meter. Multiply that by 9.8. And here's the thing I think is amazing. You would have a column that is about 10.3 meters tall. So if this was water, you would have to have one that was 10.3 meters tall. So you're talking over 30 yards would be the length of it. So you're talking about a building that's over 3 stories tall. It would just be amazing, just incredibly tall that you'd be dealing with. So you don't usually do it with water, plus water is going to eventually evaporate, so that's just not going to work, but it's just kind of an interesting concept. The next part that I think is kind of neat here is the fact that if I have some kind of fluid and it has a particular pressure, and then I use air pressure at that, you can actually create something that's kind of like a barometer where you try to figure it out, or some kind of pressure sensor. And you can find the pressure in here by actually measuring the height of this fluid, and you usually use a dense fluid. Mercury is the most common one they used to, but we use other ones now. And so I can figure those out. It also, this slide reminds us what we mean by gauge pressure. And gauge pressure is just the difference between the absolute pressure inside that fluid minus whatever atmospheric pressure is. So it's the difference between them. Interestingly enough, this all relates to how you actually drink out of a straw. If I am drinking something, most people would say I suck the liquid up the straw. I would argue that you're not actually doing. Physics never sucks. Write that right there. Physics never sucks. Instead, what you are doing is you are creating a lower pressure here. When you put it in your mouth and you increase your diaphragm, you are actually decreasing the pressure inside of your mouth, and that lower pressure, and then you have to have air pressure that pushes down on top of your fluid. That air pressure is greater than the fluid or the pressure inside your mouth, and it will cause the liquid to rise. So in essence, it's similar to this, that you're making the pressure on the outside of the fluid greater than the pressure inside of your mouth, and that's what pushes it up there. So it actually is the push of this that pushes that fluid into your mouth. It's not sucking the fluid up, it's actually air pressure forcing it in. This is kind of a neat other Veritasium video on the world's largest straw. I'm going to put that as a link as well if you want to watch it. Just kind of a neat how long the straw could be, and how actually drinking out of a straw works. Couple last little things that I think are just kind of neat additions. If you've ever had like a water bottle and you squeeze on the water bottle, we know that water will go shooting out of that thing. And the reason why is what's known as Pascal's Principle. And what it tells us is that if you apply a pressure to one point on a fluid, that pressure will get applied evenly throughout the entire fluid. And so if I had a enclosed fluid here between these two things, if I apply a pressure on this section, that pressure will transfer and I'll have the exact same pressure over here. Technically, it's actually going to be this equation because it could actually be different if you had a difference in height between the 2 points. But if they happen to be the same, then H is equal to 0, and you actually get the pressures to be the same. We use this for hydraulic jacks. That's why this picture down here for part B is kind of showing it, is you actually apply a small force over a small area, and you have a difference in height. And what you can get is you can get a much larger force over a much larger area, so you could raise a car up by actually pushing down on a jack. So Pascal's principle is kind of neat for that. The other one that we've already had is good old Archimedes Principle. And Archimedes Principle talks about the fact that if I have a section of the fluid in here that, or you're talking about some kind of buoyancy on this object, buoyancy, apologize, my pen just doesn't want to work, that it would be the difference between the force on the bottom and the force on the top. So if I have a greater force here, there's F2 and there's F1 acting on this. So the difference in there is what's causing the buoyant force. Well, if I factor out the A, I know that P2 minus P1 is equal to rho GH. So I could plug that in. I know that the H times A is really just the volume of this object. So, there's the volume, and I can replace it, and sure enough, on the right side, you end up with the weight of the displaced fluid, because this is mass times gravity, and that is the buoyant force acting on. So Archimedes' principle really just comes directly from the concept of pressure. That finishes up the first section of chapter 11, which is on fluid statics. So we've got the idea of pressure now. We're going to use that to our advantage. So I'm going to see if I can end this. Keep those little inks there and get up here so that I can actually stop this little video, and I will see you guys